Hello, welcome back to New Scientist Weekly, the essential selection of the week's science stories. I'm Chelsea White.
And I'm Rowan Hooper. Welcome to the show. This week we're getting sucked in to the earliest black hole in the universe, and we're going to look for even older black holes, older than the universe.
And staying with deep time, we're going to be talking about why we're trapped in short-term thinking and how to take the long view. And I have a story about tiles that has got mathematicians incredibly excited.
Is a mathematician excited? Like, how do they like raise an eyebrow?
I suppose they might.
We've also got an amazing life form of the week, which I've just been to see. It's the largest animal of all time, the largest land animal of all time, which made me feel very small. It was brilliant. But we're going to start this week with an unusual solution to the climate crisis. So it's a study claiming that restoring 9 groups of animals could make a big difference in the fight against climate change. Sam Wong has edited this story and joins us to explain it. Sam, how does it all work?
Hey, so as we all know, the first thing we need to do to rein in climate change is to cut our carbon emissions as much as possible. But there's going to be some emissions that we can't get rid of. So we also need to increase the amount of carbon taken out of the atmosphere by living things. So most of the time when we talk about this, we're talking about plants and algae, so forests, seagrass, kelp, that kind of thing. Animals make up a relatively small amount of the biomass on the planet, so they tend to be overlooked. But a group at Yale University think that animals can actually play a big role through their effects on the wider ecosystem.
What kind of effects are we talking about?
So herbivores eat plants that compete with trees for resources, and they pack down the soil to keep more, so that the soil keeps more carbon in, and they pack down the ice and the permafrost. They maintain grasslands that might otherwise lead to wildfires. They promote new tree growth by dispersing seeds, and they also store quite a lot of carbon in their own bodies for a long time in some cases. Predators are also important because they control populations of animals that might otherwise overgraze on carbon-storing plants if they are left unchecked. And whales are really important as well. They promote the growth of phytoplankton at the sea surface with their feces. And when they die, they send loads of carbon to the sea floor.
So how much difference to the carbon budget do these animals make overall?
So in this study, they calculated the impact of 9 groups of animals. For 6 of them, they were looking at the effect of maintaining their population at current levels. So that's reef sharks, grey wolves, wildebeest, sea otters, musk oxen, and ocean fish. And the other 3 groups, they looked at the effect of restoring those populations. So we need populations of at least 500,000 African forest elephants, 2 million American bison, 188,000 baleen whales. Collectively, these 9 groups could help capture around 6.41 gigatons of carbon dioxide annually, which is almost as much as the total amount of CO2 that people have estimated we need to capture every year in order to keep global warming to 1.5 degrees.
Well, that sounds promising, but those are huge numbers. How achievable is it to maintain that kind of population for all these animals?
So we would need to have much more of the land and the sea protected for wildlife. That means that a lot of the land we use for grazing farm animals now would have to be returned to a more natural state. Oswald Schmitz, one of the researchers, he said cattle ranchers should become carbon ranchers with herds of bison, and we should pay them for the carbon that they store rather than their meat. And we also need to address all the existential threats to these animals, so overfishing, persecution of wolves and sea otters, the fences and roads that people are building that are getting in the way of the wildebeest migration, all of these things.
And if we do all of those, will it really make as much of an effect on climate change as they say?
It's questionable. So Krista Lestay-Lasserre, who reported this story for us, she spoke to Yadvinder Mali at the University of Oxford, and he's not entirely convinced. He thinks the timescales may be too slow, and he says trying to get this into international climate frameworks could even be a distraction from the only real global warming game changer, which is keeping fossil fuels in the ground.
We've got another amazing story from the James Webb Space Telescope now, and it's spotted another object from the very, very early universe. This time, a black hole. Alex Wilkins joins us now to explain. Alex, what's the story?
Yeah, so the James Webb Space Telescope just keeps unearthing things from the very first moment of the universe. And this time, we've got our earliest black hole. So it's a supermassive black hole in a galaxy from about 570 million years after the universe began. We're currently at 13.7 billion years, so it's a very, very long time ago. It wasn't by complete chance that the researchers found this black hole. They'd actually identified the galaxy before from a Hubble survey, and they'd found that it was incredibly luminous in that region of the sky. But the thing about JWST is it's got much more powerful and precise instruments. So astronomers could actually see what was making up the light coming from that galaxy in terms of the elements that were emitting it and really sort of separate them in high definition. Rebecca Larson, who's at the University of Texas in Austin, one of the astronomers involved, told me that when she saw this characteristic signature in the readings, it was a sort of wide bar. She didn't know, in her words, what the hell was going on because it seemed to be so out of place. But she checked in with her colleagues who were sort of more familiar with supermassive black holes, and they concluded it must be the light coming from a black hole in the galaxy center.
What a moment. Yeah, that's very cool. And I imagine it helps with our understanding of the universe, but it seems a little weird to me that you'd even get a supermassive black hole that soon after the universe began.
Yeah, no, it is a little weird. There's this long-running mystery in explaining where supermassive black holes come from. We see them in our local universe, not too close to us, but we see them around us. Yeah, thankfully. And some of them are incredibly large. Like just today, there was a story about a group at Durham that have discovered one of the largest ever at 30 billion times the mass of our own sun. So they're really enormous. But we don't know exactly how they formed. There's a few different ways that they can form. Many people think that they form from stars that collapse in on themselves and then over time sort of slowly accrete more and more matter. But there's another theory that they can just form from huge amounts of gas in the early universe. These are called direct collapse black holes, but we haven't actually ever seen these. So just having one piece of evidence so far back could be really helpful.
And does that piece of evidence tell us which one might be more common?
Well, this isn't going to be what you want to hear, but it's not conclusive.
It never is it?
I know. They just keep us wanting more. So Larson told me that if it had been much bigger, we might have been able to say it was from a direct collapse. If it was much smaller, we could have said it was from a collapsed star. But it's in this sort of annoying in-between phase. But having said that, one researcher who wasn't involved in the work that I spoke to told me that the black hole is very, very massive. And in fact, it has so much mass that if it did come from a stellar mass black hole, then it would have had to grow really rapidly, given how early they found it in the universe. So it's not impossible, but the evidence is definitely leaning towards it being a direct collapse black hole.
And how much earlier can we go back in time looking for black holes? Because we've got a story this week in the magazine about the hunt for black holes that might have existed, and this is just, I can't get my head around this, but might have existed before the universe began.
Yeah, it's a pretty mind-bending concept, and I'll get to that in a second. But
yeah.
to answer your first question, we don't know how much further back black holes go. JWST has only really just started looking in the early universe, and it's really at the beginning of its sort of scientific mission. So we're hoping to find more examples further back. The telescope is capable of looking further back than 508 million years, but it's just sort of a matter of luck whether we can see a black hole that gives off enough light for us to see, and we don't know if that's possible so far back. But theorists have been exploring this whole possibility for a long time. Actually, in the magazine this week, we've had physicist Bernard Carr, who worked with the late Stephen Hawking, and he has written about primordial black holes and the idea that some of these black holes might exist before time, which, as you say, is a crazy, crazy idea.
Yeah, I mean, this might be a very obvious question, but how the hell does that work?
Yeah, no, you're right to ask. So primordial black holes, to start with, are theorized black holes that formed in the very, very first moments of the universe, before stars even existed, from sort of subatomic particles forming into black holes and sucking light in, and we don't know how large or small exactly they were, but something that if they persisted to today, and some people think they might have just evaporated and never be seen again, but if they persisted today, they could be the seed for the supermassive black holes we see. But again, we haven't seen them. And then this is where things get really weird. So there's also this idea that Carr suggests that these black holes might have come from a previous universe. And that would be the case where if the universe didn't start with a big bang, it instead started from something called a big bounce, where there was a previous universe that was shrinking, reached a certain point, and then began to expand into our universe today. And he says if there were black holes in that previous universe, then they might have been able to survive this sort of crunch, and that's what we might be seeing today.
So they would have been like large and got squeezed down and somehow made it through to our universe.
Yeah, exactly. It's a bit of a strange thing to think about.
Totally wild, yeah. It does sound very speculative. Is there any way we can ever really know?
Yeah, as you say, it's extremely speculative, but that never stops theorists trying to come up with predictions. So Carr says that one way that we could find whether these black holes survived from this pre-universe could be how many supermassive black holes we see above a certain amount of mass. So in the case of a big bounce scenario, we would see less supermassive black holes above a certain sort of limit, mass limit, because of the density of space in the previous universe and how that all propagates forward. But we just need more black holes to really tell. We haven't seen enough, and we've only been observing them recently. But if you want to read more, there is an excellent feature in the magazine this week.
And it's an absolute mind bender, and we'll put a link to that in the show notes.
Let's take a quick break. We have the second event in the new series, The Greatest Physics Experiments in the World.
Yeah, the event is Fermilab, Solving the Mysteries of Matter and Energy, Space and Time. Join Fermilab's senior scientist Don Lincoln as he explains how America's flagship particle physics facility has taught us so much about our universe and how it works.
This is an online event on the 4th of April. Go to newscientist.com/Fermilab to find out more. It's Lifeform of the Week. And Rowan, you've been out hunting dinosaurs.
So I'm at London's Natural History Museum to see the skeleton of one of the largest animals ever to have walked the earth. So let's go in. Wow. Yeah, it's hard to describe this. It is absolutely immense. So what? I'm walking underneath its belly now. This is a titanosaur. So it's a giant sauropod dinosaur. And you'll know them from Diplodocus that used to be in the Natural History Museum. And just from your dinosaur knowledge, I'm just standing underneath it now. And it's like, being underneath a gigantic truck or boat or ship. So the feet are towering above me. So this one is Patagotitan mayorum. It's a member of the sauropod group called the titanosaurs. And we've known about Patagotitan for a while, but this is the first time we've had a complete specimen in Europe. And I've got lots of questions about this, so to help me answer these, I'm joined by paleontologist Paul Barrett of the Natural History Museum. Paul, what is it about the sauropods that allowed them to be so big? Because land mammals, we don't get anywhere like this, do we?
No, they just don't. So they have a really unique combination of features that allow them to excel even the very biggest mammals in size. Some of those are just structural. They have these limbs that are basically like huge pillars that are capable of holding up that huge weight as just columns, really, being able to deal with that massive mass just looming over them.
What is the weight we're talking about here?
So this animal, we think, weighed about 57 tons. So that's about the same, just put in context, of about the same as 8 very large bull African elephants.
Yeah.
So these things are having to hold up an awful lot of weight. So big, strong limbs under the bodies, very large, powerful muscles to help keep those limbs in place and to stop them kind of legs splaying apart and them face planting on the ground. Yeah. And in addition to that, they could grow really fast. So these aren't animals that are taking decades and decades to reach these sizes. They're reaching these massive sizes within maybe 30 years.
Right. I was going to ask about that because I saw an egg on the way in and it was surprisingly small. I'd imagine maybe the egg was going to be the size of a car or something, but they're born tiny relatively, aren't they?
That's absolutely right. So these things actually hatch out of eggs that are not much bigger than a grapefruit, sort of about 12, 15 centimetres across.
Yeah.
And they hatch as animals that you could very easily hold in the palm of your hand, like little sweet tiny sauropodlet dinosaurs. And these things then just keep piling on the weight, and They do that incredibly quickly. They kind of speed up as they get in towards their teenage years, and it's really when they're teenagers, like with humans, that they put on all that extra kind of mass to really bulk out into what we see in the adult.
Okay, and so this was living 100 million years ago around. did we have flowering plants back then? I can't. What were they eating?
So we did have a few flowering plants then, but they were pretty rare. It's not like today where almost everything we look at is a flowering plant. No. So it might have occasionally nipped at a couple as part of taking big mouthfuls of food. But this is mainly living in an area that's composed of open forests made up of things like monkey puzzle trees. So to some extent, slightly familiar, because we'd recognise a lot of the types of trees that are around, and there are many ferns forming kind of the undergrowth at that point. But in other respects, slightly unfamiliar in that we wouldn't get much colour. For example, there wouldn't be much colour from flowers mixed in with this. Yeah. So a very green landscape, and these essentially living, walking hoovers that are sucking up as much plant food as they can.
Well, let's have a walk underneath it while we talk. So most of these titanosaurs we know from Argentina, what's now Argentina, don't we? So what is it about there that is good for these things fossilising? Because I imagine it's hard to fossilise something on this scale.
Yeah, absolutely. So there are only a handful of these really giant titanosaurs. They're all very close relatives of each other. And we just don't understand why. So it's been suggested maybe there's something odd about Cretaceous Patagonia that fostered this really large size. Maybe there's something about the plants or something about the environment. But as far as we can tell, there's nothing particularly unusual about it. So we're really at a loss as to understanding. I mean, it could simply be that we did get these other giant dinosaurs elsewhere in the world, and we simply haven't found them yet. I mean, Patagotitan was only named in 2017. And you might think, how do you miss a 37-metre long dinosaur? But it just proves, it comes down to kind of the good luck or bad luck you have when you're out fossil hunting as to what you might find. Yeah. So who knows? We might find them elsewhere in the world, but at the moment, they're a peculiar feature of the dinosaurs that we find in South America.
And am I right in thinking that the titanosaurs have got this really weird variation in scale in their group, from actually quite small for a sauropod to then the biggest we've ever seen?
That's absolutely right. So sauropods are a group of dinosaurs that we think of in general as fairly large. Right. So your average sauropod is an animal that probably weighs somewhere between 15 and 20 tons and is probably about 20 or 25 meters long. Yeah. Titanosaurs actually exhibit both extremes. They're the main group, they're the biggest group of sauropods in lots of ways. There are many different types of them, and they experiment with body size. So some of them, like this guy here, experimented at the large body size end of the range, but we also have what are called dwarf titanosaurs. These are animals that are descended from much larger bodied ancestors that, because they lived on islands, actually shrank in size over evolutionary time. So the smallest titanosaur has a hip height not that much off ours and would have only weighed a few hundred kilograms when it was an adult, whereas one of its cousins, this guy, is at least 100 times heavier.
Yeah, like being underneath it, it's still hard to comprehend the size of it, that something on this scale was roaming around. Now, in New Scientist, we've written about, I don't know whether you could call it a conflict among paleontologists, but a discussion that there may be even bigger ones out there than these titanosaurs that we found so far. What do you make of that?
It's entirely possible. I never say never. It could be that in the rocks there is, at the moment, an even larger animal waiting out there to be discovered. But what I do think is unlikely is that we're going to find animals that are, say, twice the size of this. I think we're starting to get towards what might be a theoretical upper limit for life on land for some of these things. Bone and muscle have particular mechanical properties, can only be stretched so far. And I suspect we may well find animals a bit bigger than this. But it's interesting that of all the giant dinosaurs we're finding, most of the sizes of them are now starting to settle down around the same limit of somewhere around 60 tons. And it looks like we might be starting to strike that kind of maximum with these animals.
Well, it feels a bit greedy asking you about a bigger one anyway, because when you're walking under... I love the way you can walk around it here, because you really get a sense of just the colossal nature, the titanic nature of these things.
Actually, one of my favourite views of the thing is standing directly underneath.
Where we are now.
Centre, exactly, just below its hips and looking straight up. Yeah. Almost looks like a boat that's been turned upside down, or even like the top of a medieval cathedral with all of the ribs and the vertebrae acting as kind of flying buttresses for the animal. So I think actually standing directly under it is one of my favourite places to get a sense of just how big it is. The animal's really wide. It's wider than some of the rooms in my house. And I think if you imagine how much space there is under here, you could probably fit about 25 people standing under here in the space between its legs.
That was Rowan at the Natural History Museum in London, and the Titanosaur exhibit is now open to the public.
Next up, we've got some of that hot maths news. The news that's made mathematicians get all hot and bothered.
We certainly do. I love this story. It's the discovery of a single shape that can be used to cover a surface without ever creating a repeating pattern. So if you think about a bathroom wall or floor, your classic square or rectangle tiles form a regular repeating pattern of shapes. But now, at last, researchers have found a specific shape that can be used on its own to tile a surface but never form a repeating pattern.
I mean, it actually is quite exciting. What? But how? I mean, how? And what does the tile look like? How can? Yeah, it's mad.
Yeah, well, it's actually quite a simple shape. It has 13 sides of varying length, and the team who discovered it have named it the hat.
Does it look anything like a hat, or is
I mean, not in my mind. I can't find the hat in it.
Yeah. So okay, this is big news, right?
Yeah, it's really big. So researchers have been looking for something like this for decades, but no one even knew if it was possible.
So we did know that you could tile a surface without repetition, but you'd have to use more than one shape to do it. And what they've done now is find that you can do it with just one shape.
Yeah, exactly. So the mathematician Roger Penrose discovered in the 1970s that two shapes could be combined to create an infinite, never repeating pattern.
Well, we were talking about this in the office, and Penny told me that in her bar at Wadham College, Oxford, the patio was tiled with Penrose tiles. Which,
of course.
Yeah, well, I mean, even when you're drinking at Oxford, you're learning stuff. But how did they find the hat then, this hat?
Well, Chaim Goodman Strauss at the University of Arkansas and his colleagues used powerful computers to eliminate large numbers of candidate shapes. And then they applied their own human experience to finding a shape that would work and developed a mathematical proof for it. So much of what has made finding a single shape that tiles aperiodically really, really difficult is that you need to be able to prove that it really doesn't ever repeat. In Chaim's words, a human had to be involved in constructing a proof that a human could understand.
I mean, I'll give it to the mathematicians. That's all very cool. I have to ask, does it have any uses, this discovery?
Well, it's possible that we could use aperiodic tile shapes to design materials that have, unusual properties, maybe something that's really strong. And of course, it could make a really great tile for anyone who wants, a nerdy bathroom makeover.
I do, now you've said that, actually. We'll post a link to Matt Sparks' story on this, where you can see the shape of the hat. Decide if you think it's a hat or not. We'll post a link in the show notes.
Now, as we heard in the black hole story, physicists don't have any problem thinking about deep time. But for the rest of us, our inability to think about the long term is a real concern. Many of the most serious problems we face are the result of our tendency to focus on the present at the expense of the future. But Richard Fisher says we can escape this trap by confronting how we think about time. Richard is a science journalist at the BBC and has just written a book on this, The Long View, Why We Need to Transform How the World Sees Time. Rowan went to an appropriately old place to meet him.
I've come to Richmond Park in southwest London. Seems like an odd place to come to talk about time, but we're looking at an ancient barrow, a burial mound, in the park. So it's a Stone Age barrow. I think it's like 3,000 to 5,000 years old. And whenever I come here, I like to think about the people who lived here thousands of years ago. But Richard, your whole book is about thinking about deep time. So tell us how it came about.
So my book, I guess, began with reflecting on the future, I suppose, like thinking about my daughter and her path into the next century. So she was born in 2013. And after she was born, all sleepy, blurry-eyed, I started to think about, okay, well, what is her life going to look like? So she stands a pretty good chance of reaching the next century, which blew my mind. She'll be 86 years old, seeing the fireworks going off on New Year's Eve. And that reflection about like how our generational ties reach into the deep future and the deep past kind of inspired me to start thinking about like what is it to have a long view, what are the causes of short-termism within society, and how do we embrace that deeper view of time. And so it's great to come here today to Richmond to kind of like think about this because like there's all sorts of signatures of deep time in this park.
So I guess one thing that we often talk about with our inability to think about deep time is when we think about the climate crisis and we can't plan far enough ahead. Why can't we project to the future like that?
So I've got a piece in New Scientist. In that piece, I talk about kind of like some of the reasons why it's difficult to project yourself over time. There are many external reasons, like cultural reasons, why we kind of think shorter term or longer term, and there are also kind of many internal ones. So the external ones in the book I call temporal stresses. So these are kind of inventions of the culture that we live in that lead to a short-term view. So one of the examples in the business world is the quarter. Quarterly capitalism tends to lead business leaders to start to only think about the next 4 months. So that's an example of an external temporal stress. On the internally, though, we also have lots of psychological habits and biases. One of the most well-known is the kind of the marshmallow test bias of it being unable to delay gratification. Seeing a single marshmallow in front of you and taking that rather than waiting for two down the line. That test has its flaws, of course, but it is a kind of very simple way of showing that people struggle to imagine their future self and how they might benefit if they kind of delay that gratification.
But you make the point that we haven't always been this bad about projecting to the future, right? So is that because we're at peak capitalism and just wrapped up in all that stuff and we've lost the ability or, neglected that part of ourselves?
So one of the things I wanted to look at was how did past cultures think about time? What was their sense of past, present and future? How did the Romans think about it? People in the Middle Ages. There is evidence that, you can see very clearly that past cultures were able to kind of plan ahead. So you look at Stonehenge or the Great Wall of China, it was clear that thousands of years ago it was possible to build these extraordinary things.
On the back of slave labour, though, maybe.
Yeah, that's true. Well, another example is this well-known in kind of long-term thinking circles is the concept of cathedral thinking, where people in the Middle Ages started to build cathedrals that they knew would not be finished, and the next generation would pick up the baton and finish it. There's cathedrals still in Europe that are not quite finished. It's still going. But it was a different time. Things moved slower then. The sense of progress was slower. People knew that their grandchildren would likely live in the same world as them. So it was easier to kind of plan ahead and think into the future. We live at an extraordinary time when things are changing so fast, exponentially, through progress in technology that we have no idea what the world will be like for our grandchildren. And so that setting, just the culture that we live in, makes it difficult from the start to think longer term. One of the things I write about in the book is what I call temporal windows, which are kind of ways to kind of access deep time that are tangible in your local surroundings. So, we're sat on a barrow that's thousands of years old. I've cycled past this many times and never noticed it. I didn't know it was here until our mutual friend Tom told us about it. But now I know it's here, and I have a sense of that there were people that were once walking here thousands of years ago, and it's a temporal window to a different time.
Yeah. It's a really personal book, and that's something I really enjoyed about it is that element to it, because you mentioned becoming a father and how that influenced you. And you lost your father as well, and perhaps both those things, have influenced your thinking about deep time. And maybe it's like with the climate crisis, making it personal for people is a way of engaging them, and maybe that's a good way of getting people to think about deep time, is just to think personally what it means to them.
There's a chapter in the book where I write about the experiences in my life where I've kind of lost people, so losing my dad or losing my baby son a few years ago. That was midway through writing the book, actually, and those experiences kind of led me to reflect on what it is to think with a long-term view, and I think that there's an approach which has resonated with me, a kind of philosophy that dates back to a comment from Edmund Burke in the 1700s. He was a political thinker, and he wrote about society being a contract between those who came before us, those who live today, and those who are still to be born. And that idea of thinking about time situated in the ties that we have with each other that extend across the generations, that's the approach that I'm most drawn to. To compare it with long-termism is a kind of top-down population ethics view. This kind of more generational time view kind of starts with, okay, I'm going to think about my daughter and her life into the 22nd century, and then her children after that, potentially. In a few steps, you're in the 23rd century, and you can go backwards as well. You can kind of think about your own family ties going into the past, and then when you think about family trees, extending backwards, eventually all our trees enmesh with one another, and so we're all kind of interrelated. There was a common ancestor to all of humanity that lived as recently as 3,000 to 4,000 years ago, which I find extraordinary.
Yeah.
So that sense of being situated in the human and the personal is the start for me, definitely.
Great. Well, thanks, Richard. Let's walk around this barrow and see if we can find some flint tools from our common ancestor 3,000 years ago.
That was Richard Fisher talking about his book, The Long View, Why We Need to Transform How the World Sees Time. And he's also written a piece for us about it. We'll post a link in the show notes. That's all for this week. Thanks to our guests, Sam Wong and Alex Wilkins. And thanks to you for listening.
Do subscribe to our show and urge everyone you know to listen. And thanks for joining us. We'll see you again soon. Bye for now.
Bye.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.